my name is Joseph Nyamogo, and I'm a student at the University of Florida Department of Electrical and Computer Engineering. And my presentation today is about improving non-orthogonal multiple access bit error rate using successive interference cancellation in Simulink. So I'm going to start with the presentation, then I'll do the simulation. All right, so great. All right. The first step is, because of the increased wireless devices that are joining networks or cellular networks, there's research into how to accommodate all these devices. So the different ways that have been used are time division, multiple access TDMA, code division, multiple access CDMA, frequency division, multiple access FDMA, space division, multiple access SDMA, and orthogonal frequency division, multiple access of DMA. And all these technologies have limitations. So, to improve on the limitations, different areas of research are being pursued that have to do with cost reduction, increased energy efficiency, increased quality of service, increased throughput, increased reliability, increased data rate, increased spectral efficiency. One method to improve the spectral efficiency is multiple input and multiple output MIMO. So MIMO operates by simultaneously transmitting and receiving data by utilizing multiple antennas, and it does this by exploiting spatial beams and multipath trajectory by assigning different users to different beams. One disadvantage of this is it's difficult to know the state of the channel at the receiver. Another technology used to increase data rate is millimeter waves, which lie between 30 gigahertz and 300 gigahertz. Now, because the high frequency, there's increased data rate, but they also suffer from high attenuation because of the shorter wavelengths. Now, another technology to try and solve the previous technology, FDMA, CDMA, TDMA, that we saw before, which are orthogonal multiple access technologies, the technology is non-orthogonal multiple access, NOMA. So in OMA technologies, CDMA uses specific codes for different users. TDMA uses specific time slots for different users, and FDMA uses specific frequencies, and that's how interference is avoided. Because of that, OMA is inefficient. So NOMA utilizes all the resources, for example, frequency at the same time, simultaneously. And this can improve the spectral efficiency by the users the user with the highest priority using the resource, for example, a channel, and the user with the lower priority not using the channel. Now, to remove interference between users in the same channel, successive interference cancellation, SIC, is used. Here's an example of the NOMA model that we're going to use. See, this is OMA with different frequency slots, and the power is the same. But in NOMA, all the frequencies are utilized simultaneously, but different power are allocated to different users. So the two techniques are power allocation and scheduling. In power allocation, different users get different power assigned to them depending on the throughput and fairness required. And scheduling is used depending on which user has a higher priority with respect to the required throughput. Now let's look at a simulate to show how SIC is used to cancel interference. We'll have two systems, one with and one without SIC. So we'll simulate a downlink from base station to two users. First user UE1 is the near user. The second user UE2 will be the far user. The channel gain of UE1 is H1, will be H1, and the channel gain of UE2 is H2, and the channel gain H1 is greater than E2. That's the relation. Now X is a signal from the base station to both users. Phi1 is the power allocated to the near user EU1, and Phi2 is the power allocated to the far user EU2. And Phi1 and Phi2 are related by Phi1 less than Phi2. So the power allocated to the near user will be less than the power allocated to the far user. S1 is the message sent to EU1, S2 is the message sent to EU2. Now here's an example of the near user UE1 and the far user UE2. Y is the message that's received by any user in the channel. H is the channel gain, X is the transmitted message, and N1 is the noise. Here's an example of a near and far user without SIC. So this is our base transmitter, and the near user will have a higher power because it's closer to the transmitter, and the far user will have a lower power, 0.2, because it's far from the transmitter. Both messages are added into the channel. And here's an example of a NOMA model with with SIC. The near user A1 gets a lower power because it's closer to the transmitter. The far user is assigned a higher power, but because the higher power interferes with the near user, the user subtracts the message from the far user before decoding its own message. So in this way, it makes it easier to decode its own message. Now let's look at the result of a near and far user without SIC. Now you can see the far user without SIC has a worse bit rate than a near user with no SIC, and this is exactly what's expected. Here's another graph of near and far user with SIC, but we superimpose it on the previous graph. Here's a new user with SIC. The bitrate has improved much better than the far user without SIC. Now here's the far user with SIC, and the bitrate has improved than the previous case, and in some instances the bitrate is better than the near user with SIC. And this is one of the challenges of a NOMA system, is how to assign the appropriate power profiles to near and far users, and that could be another area of research. So the next thing we're going to do is next thing I'm going to do is look at the simulation. Let's see that, and let's go to our project here. And let's open let's go to a Simulink. Let's go to a Simulink here. Now let's open this model. Now, let us, these are near user, so this 0.9 is the near user power because it's closer to the transmitter. These are transmitter. 0.2 is the far user power. And let us go to the MATLAB interface and start our BER tool. So let's see here our theoretical. Let's start with the theoretical values. You can we'll set this to 0 to 12 AWN DPSK modulation order 2, and this is going to be 0 to 12, and we're going to browse the model. Correction. Here is Simulink, and we're going to browse the model, which is going to be Simulink with no SIC, and it will open. The BER variable name, we'll get it from the name from here. Let's look at the parameters. What parameters? Near user NOMA. So let's go to our BER tool. That's going to be near user NOMA, and we're just going to have this change to 0.4, the number of bits, and let us run. All right. So let me see here. So I don't have, this is a simulation. I don't have the theoretical here. Let us plot our theoretical. Here's our theoretical value. Let's go ahead and move this to our, let's put this past. And let's go in here and change. This is a new user. New user, no. New user, no SIC. And let's go in here and change our file user here. We're going to go in and, all right, go to the BER tool, and now we want to change this to our file user, and let's run and look at a plot. And we expect the file user to have a was-BER range. And let's just go ahead and file user, now SIC. Now let's go in and change. Let's look at the new model we are looking at, and our new Simulink model is here's our near user with SIC. So the power is 0.4 for the near user because it's closer to the transmitter, and 0.8 for the far user because it's farther away from the transmitter. And this is our SIC that we use to cancel out the message from this from the far user, which appears as noise to the near user. So when we go back to our BER tool here, and we browse, and we're now going to take the NOMA with SIC, and once again let's start with the near user, which is this one, and let's see and run, and let's see. That's our near user, and note how our BER has improved much better than the near user, the SIC. Now let's just go and rename this to so here's our new user, and let's go back and change our variable name from the far user, and now we're going to take using this variable name, and let's go and change this and run, and let's observe the BER rate of the far user. As you can observe, the BER rate of the far user, and let's just go and rename this to far user SIC. You can see the BER rate of the far user is much better than a lot better than the BER rate of the far user without SIC, but the BER rate of the far user in some instances it's certain SNRs it's better than the BER rate of the new user with SIC, and this is the challenge with NOMA, coming up with a good SIC strategy and power allocation strategy. Thank you.